Hello, good morning, good morning, good morning, my warriors. Welcome aboard. This is Shreyas here, your physics master teacher at Vedantu going live. How is everyone? And I hope you can see me. I hope you can hear me loud and clear. And if you can, do let me know by putting a thumbs up, by putting a yo, by putting a smiley, by putting a fire symbol, or by putting a nice heart out there. Yes, Karthi, I do remember. Hello, Tornado. Nice to see you back. Hello, Shreyas Kapri. Hello, Kavi. Hello, SS Bhupan. Hi, Sharv. Hello, Venu. Hello, everyone. Good morning, good morning, good morning. So, guys, nice to see you up in the morning. It's a very good habit to actually wake up even before this and finish all your, morning activities and get to studies, get to classwork and start solving problems and attend sessions by 8:30, 9 o'clock. That's a good time to start your actual studying activity. And that's why I want you guys to get into the habit, because I know most of your classes online especially are in the evening. Very few people actually get up in the morning. In fact, I am a morning person. I get up every day at around 5:36. I go for a jog, run for 3-4 kilometers, and then I come back, then I start checking my mails and all the other things. So I hope one day you too will get inspired and start working out, and start getting up early and finish all your activities early in the morning and plan your day accordingly. Trust me, all those people who face time management issues, most of your issues will go away just by doing few of these pointers. Nice. Welcome aboard, Dev Prasad. Hi, Achintya. Hello, Chitra. Hello, Saurabh. Hello, Devi Prasad. Hello, everyone. Hi, Fari. Welcome aboard to this channel. And guys, I'm Shreyas and I've been teaching for a very long time. And I really hope that whatever, experience and the knowledge that I have acquired over the past almost more than a decade is going to help you out, because it has been helping a lot of students. And many of my students are right now in IITs, NITs, you name it. And I really want you guys to get there. And I'm pretty sure you will fall in love with physics when you start attending my classes in the long-term batches as well. So, well, I actually teach on VNTUs. And right now we are making sure that you guys are not left unattended. So this session is for both 2021 and 2022 students. That is the 12th standard passing out and the current 11th to 12th moving students who have some idea of magnetism. So we are going to brush up on the topic of magnetism. We are going to see some good problems and the entire chapter, like sources of magnetism, magnetic effects, Lorentz force, all of these things, force between wires, and magnetic dipole. These concepts will be covered in today's class. So in case you are new to the channel, first of all, hit the subscribe button. And those of you who are following us on Catalysis, do not forget, you will get the long-term batches, regular sessions on all the 11th, 12th topics, including the crash batches for the 2021 students on VNTUs. Keep that in mind. So on VNTUs, you need to go ahead and follow us out there. Make sure you hit the subscribe button so that you do not miss any of the updates. So are you guys ready to start the class? Yes, Srividya, this is for NEET students as well. So the content has been designed keeping in mind there are NEET as well as JEE main students. So it's for both. Yep. So Shohan, this is actually one shot. If you realize this is actually one shot, but I'm taking up the important topics first, the most in demand topics. And from the beginning, if you want one shots, there is a 0 to hero series on VNTUs, and I'm currently doing rank booster series also on VNTUs. You can check that out. Okay, cool. Let's get going. So everybody says super ready, Captain. All right, so let's get going then. And the first thing I want to start with is the revision of the basic laws, so that you have all the formulas. It's a good practice to keep writing whatever theory pointers, formulas I give you, so that when you solve problems, you can look at it like a cheat sheet and use those formulas for solving the problems. Keep that in mind. Now, Oersted demonstrated that whenever you have a current carrying wire it produces magnetic field around it. Now that formula is given by Biot-Savart's law, and what does it say? If you have a current carrying wire, okay, you can see this is a wire carrying current, each element out of that wire produces magnetic field. So say for example, you are here. I want to know what's the magnetic field here. I need to find out what's the magnetic field due to this element, this element, this element, that element, that element, add up all the magnetic field's contribution due to each element, and that's how I get the total magnetic field at a point. So the formula for an elemental contribution, the contribution due to an element at this point, is given by this. First of all, let's define these terms. dl is the length of the element, I is the current flowing through it. dl has to be in the direction of current, keep that in mind. dl element will always be in the direction of current. Next up, from here to here, I draw a position vector, that's the distance between the point and this curve. So this is position vector, and r hat is nothing but a unit vector in that direction. And dB is the magnetic field produced by this element at this point. Is everybody clear up to here? Let me know. Okay, so this is the element producing magnetic field dB at a position r, okay, from that wire, and the unit vector in that direction is r hat. Remember, by vectors algebra you would have studied this. R hat is the vector itself divided by the magnitude. Okay, so what's the formula, guys? Well, the formula, okay, one second. Yep. Yeah. The formula for Biot-Savart's law, dB, the magnetic field due to that element, is given by mu naught by 4 pi. Okay, so that's the constant. I will talk about that constant in a bit. I dl cross r hat divided by r square, and this constant is nothing but 10 to the power minus 7 SI units. That's what you should remember. Okay, this is r square, this is dl cross r, look at that. And if you want to find the net field will be integral of each of the contributions. All the contributions need to be summed up, need to be added for you guys to get the total magnetic field at that point. Now, the another thing that you need to know is that, okay, let's look at the direction. Yes, let's look at the direction. This is cross rule, so let's use our right hand thumb rule for vector product. In case you remember, if there was a vector A and there was a vector B, and if it was A cross B, you point your fingers in A, move towards B, and see where the thumb goes. That's how it works. So dl is here, position vector is there, dl is there, position vector is there. Okay, so dl cross r, obviously I cannot move my hands backwards. I cannot do dl cross r like this. I cannot go like that. So go via the shortest route. Don't go like this. Okay, it's a long route. You need to go from dl cross r. Look at that, dl cross r. So first put your 4 fingers. I am behaving as if I am one of you. So put your right hand like this. dl is there, r is that way. So dl cross r, see where your thumb is. See where your thumb is. The thumb is going inside. So that's why the dB vector has a cross, because it's a vector going inside. If it was a vector coming towards you, I would have shown it like this. This is towards you. This is towards you. Remember that. And this one is away from you. This is away from you. So it's going away from you. I hope this direction is clear. Everybody clear? Hello, welcome Ankit. Nice to see all the lovely hearts out there. Can we start JEE Mains PYQ Sprint series? In fact, many of the questions ran are from previous year questions. Some of the questions are most probable questions, very important questions for JEE and NEET. These questions have been chosen, have been handpicked, keeping in mind JEE Mains and your NEET examination. Very high probability questions. So in fact, even the previous session which I did, the marathon session, all right, on center of mass, collisions, whatever, all these things have, all the previous year questions as well as a mix of important questions as well as most probable questions. Sir, at angle of sine theta, So Karthi, if this theta is given, then this dl cross r's magnitude will be dl r, okay, hat sine theta, magnitude. So this will be only the magnitude, but remember r hat is a unit vector. So the magnitude of r hat is actually 1. So actually speaking, it will be dl sine theta. Think about it. Is that clear? Is this concept? So dl cross r will become dl vector's magnitude, r vector's magnitude, and sine theta. But r hat is 1 because it's a unit vector. So it will be just dl sine theta. That's how it gets. Okay. Definitely, Venu, who told you cannot get? Okay. So I have put up all the things in the PDF, and it's all there for you so that you can download it later on. Next up, for a straight wire. Now these are the formulas that you need to know. Okay, let's see. What are the formulas? Number 1, if you have a wire and you are at a distance r, the formula which you get via integration. So the formula I'm going to give it to you, but before that, the terms. I am here, okay, I'm at point P. This is a wire. It's not infinite. It's not. It subtends an angle alpha and beta from the perpendicular drawn to the wire. So what you need to do, you have a wire, you are here, you want to know what's the field. Drop a perpendicular, measure the angle subtended by the ends with the perpendicular. That's alpha and beta. Now comes the formula. Yeah, the formula for magnetic field is mu naught I by 4 pi r sine alpha plus sine beta. This is very important. Yes, mu naught I by 4 pi r sine alpha plus sine beta. Remember this. This is going to be very useful for finite wires, and in fact also useful for infinite wires. If the wire is infinitely long, these endpoints will go to plus and minus infinity. The angles alpha and beta will expand and it will each become 90 and 90 degrees. So alpha will become 90, beta will become 90. Now what's the value of sine 90? Sine 90 is 1. Sine 90 is again 1 over here because both alpha and beta are 90. So 1 plus 1 is 2. And 2 and this 4 will cancel and only 2 will remain here. And that's why for an infinitely long wire, you will get this as mu naught I divided by 2 pi r. Okay, that's how you get for the infinite wire. This formula is going to be very useful for finite wires, trust me on that. Okay, and also infinite wires. Sometimes you get questions on semi-infinite wires. Now, what does it mean is that, so let's say I have a semi-infinite wire. So what it means is that you are over here and this wire extends till infinity and it is carrying some current I. You are over here at a distance of r at this point P. Now what you need to figure out is what is the value of alpha and beta in this case. Come on my warriors, figure this out. What's the value of alpha and what's the value of beta in this case? The wire starts from here, it's not going till minus infinity and it extends till infinity. So guys, what's the value of alpha? What's the value of beta? Come on, let me know in the chat box. Come on my warriors, what do you think is the value of alpha? Very good, Clay Tsunami. Alpha is 90 degrees and beta is 0 degrees. So if you substitute it over here, you're going to get mu naught I by 4 pi r. Sine 90 is 1, sine 0 is 0. So you're just going to get mu naught I divided by 4 pi r. That's it. That's the answer. Correct. Beautiful Priyanka, beautiful Karthik. Very good Yalini, very good Shreyas Sir. Excellent. So the answer for a semi-infinite wire will be mu naught I by 4 pi r. Okay. So that's with wires. And direction, very simple. I'll tell you what. See, just do this. Imagine you are holding that wire. Just imagine you are holding that wire. So just hold it with your right hand. Okay, hold it with your right hand. See how your curled fingers are going. See my fingers. Do you see over here it's going inside? So on this side the magnetic field will be here. The magnetic field will be here. Do you see on this left side it is coming towards me? So the magnetic field will be like this on this side. So it depends which side of the wire you are if the current is going like that. If the current was going, let's say like this, let's say the current was going like this, then again hold the wire like this. Hold the wire, hold the wire. Do you see the fingers? On the top, they are coming towards you. So the dots will be here. Yes. And do you see below? The fingers are going inside. So that's why the crosses will be here. That's how it works. Yep. So that's how you get the direction. Very simple. Just imagine you're holding the wire, okay, in your right hand. And remember, the thumb should point in the direction of current. Okay, because then you'll be confused, sir, should I hold it like this or should I hold it like this? Always point the thumb in the direction of the current. Yep, that's how it is. Hello Gayatri, welcome aboard. Okay, now the next formula for a circular loop. If you have a loop carrying current, it produces magnetic field around it, and that magnetic field looks something like this. This magnetic field looks something like this. Okay, it will be something like this. This is how the magnetic field lines look like, by the way. Okay, and they will continue, by the way, and it will go like this, and it will go like this, and it will come like that. So understand, it continues, okay, something like this. Yeah, so this is how the magnetic field lines look like due to a loop carrying current. Now the only formula you need to know is the formula for magnetic field at the center or on the axis, basically anywhere on the axis. So this is the axis. Nobody is going to ask you. In fact, it's not a part of JEE or NEET where you'll be asked what's the field here. No, nobody will ask you. Okay, so field on the axis. So there is a very simple formula. Let's see how many of you remember this. Magnetic field at the center and at the axis. In fact, you can get to this formula, the center formula, okay, from here to here, by just substituting the value of x as 0. Okay, so remember this formula, mu naught I r square. R is the radius, 2 r square plus x square whole raised to 3 by 2. So r square plus x square is raised to 3 by 2. Now if you substitute the value of x is over here, okay, the value of x as 0, that means you are at the center. You are at the center, guys. So r square raised to 3 by 2. Think about it, r square raised to 3 by 2. Won't it just be r cube? Won't it just be r cube below? And r square is already there in the numerator. So they will cancel and you will just get 1 by r. So that's what you get over here. Mu naught I by 2r. So that's how you get this formula from this formula. These formulas are very, very, very important. JEE NEET perspective. Yes. Please remember this. There can be direct questions on this. Yeah, please remember. If the loop is not complete, let's say it's only a part of the loop, okay, it's only a part of the loop, then the field due to an arc will be, so the field due to an arc will be the field due to the complete loop, okay, multiplied by, think how much angle it is subtending. Let's say it's some theta. Now imagine 2 pi radians gives this much field. So theta radians will give how much field? Just multiply by the fraction. So theta divided by 2 pi. So that's all you need to do. I hope this is clear. Is everybody clear about this? Yeah. So just need to multiply it by theta divided by 2 pi because that's your fraction. That's the fraction of the arc of the complete circle. That's it. Okay. One last thing, the direction. Now the direction, look at this. Look at the current. The current is going like this. So curl your fingers in the direction of current. Whatever bends, you curl your fingers accordingly. The current is bending like this. You can see the thumb going up. So that means the magnetic field will be in this direction. Yeah. And by chance, let's say the current was like that, then curl your fingers like this. You will see the thumb going down. So the magnetic field will be like this in this case. So that's how it works, guys. So, use your right hand, that's all. I do not give any left hand rule, left foot rule, neck rule, and God knows swimming rule, corkscrew rule. All these things are, not needed for all of you. I mean, just keep it simple. Just always use your right hand. That's all you need to know. Okay, let's see how many of you can do these questions. So now that we have gone through theory, we'll see some questions, again some theory and some questions. So that's how our lecture is going to proceed, so that I can ensure that you guys understand everything. So this lecture is going to be a little bit long, okay, for around 1.5 hours or so, okay. So please make sure that you have adequate supply of food and water around you. Okay, so choose the correct sketch for the magnetic field lines of a circular current loop as shown in the figure. Think about it, it's very easy. Okay, the correct answer is actually A. Beautiful, guys. I'm really proud of you. Really proud of you. So how it works is basically, let me tell you, you have this loop, okay? At this point, okay, at this point you can see that the current is going inside. So I put a cross here. And at this point I see the current coming outside. So that's why I put a dot here. Now obviously the magnetic field lines, because of that, use your right hand rule. Yes, curl your fingers in the direction of current. The thumb goes up. Naturally, the magnetic field should be like this, which is nothing but this option. You can see, if you see it from the side, you'll exactly see this one, option A. Yeah, that's what you're going to see, the sectional view. Now look at this question. There is a long wire which has radius r, but it is in the form of a semicircle and it carries some current. What is the field at this point? Remember, the current comes like this, goes like that, and goes like this. Okay, let's see how many of you can get this. First of all, मुझे ये बताओ, come on guys, tell me, if so both the angles were right now 90 degrees and 90 degrees, okay, both the angles were 90 degrees and 90 degrees, but the moment I go over here, what will happen is these two angles, look at that, okay, these two angles which are there, one of the angle will almost become like 90 degrees, I don't know if you can visualize that, and the other angle will become minus 90 degrees. Actually, one angle will become plus 90, other angle will become minus 90. So when you do that sine 90 plus sine of minus 90, it will cancel out, it will become 0. That's what actually happens. That's what actually happens. So hence, you will see that whenever you are on that axis of that wire, the magnetic field will be 0. The magnetic field will be 0. Okay. So hence the contribution of the field is only because of this. Only this is contributing. Only this is contributing. Yeah, only this is contributing. Keep this in mind. Everybody clear till this point? Hence, what is the formula for magnetic field at the center? At the center is mu naught I by 2r, and I need to multiply by half because it's half of the circle. So exactly half of that magnetic field will be here. Do you guys get it? Yes. So hence the correct answer will be option C, guys. Mu naught I by 4r. That's what you get. Yep. So keep this in mind. So semicircle will have half the contribution. So a lot of people get confused what to do with the straight wire. But remember, the straight wire will not have any contribution on the axis. Okay, keep that in mind. Okay, let's get going to the next one. Let's see how many of you can get this. Now the current comes like that. There is a small tiny gap. Ignore that gap. But the current goes like this, like that, and then goes like this. So the question is, what's the field at point C? सर JEE विद यूट्यूब हेल्प से निकाला जा सकता है क्या? यस अनुराग शर्मा, बिल्कुल निकाला जा सकता है, बट उसके लिए तुम्हें बहुत ज़्यादा डेडिकेशन चाहिए. यू नीड लॉट ऑफ सेल्फ मोटिवेशन. प्लस यूट्यूब में you get all the kind of content. Obviously you should follow few channels only, don't follow many channels. अगर बहुत ज़्यादा channels देखोगे फिर अपने आप ही confuse हो जाओगे, because there is lot of material available. तो वो एक चीज़. दूसरी चीज़, तुम्हें बहुत ज़्यादा प्रैक्टिस करना पड़ेगा बुक्स से, एंड डाउट्स क्लियरेंस के लिए यू नीड टू हैव सम ग्रुप ऑफ स्टूडेंट्स हु आर सेल्फ मोटिवेटेड, बिकॉज तुम्हारे डाउट्स भी आएंगे, वो डाउट्स भी तुम्हें क्लियर करने पड़ेंगे. ओके, एंड एक और चीज़ जो करनी पड़ेगी तुम्हें, यू विल हैव टू गिव अ लॉट ऑफ मॉक टेस्ट. बहुत सारे मॉक टेस्ट देने पड़ेंगे. नाउ व्हेन यू आर इन अ रेगुलर पेड प्लेटफॉर्म क्या हो जाता है, ऑलरेडी देयर आर टेस्ट एट वेरी रेगुलर इंटरवल्स, सो यू नीड टू गिव मॉक टेस्ट. द ओनली प्रॉब्लम इज फिर तुम्हें अपना रैंक या फिर एग्जैक्ट कंपटीशन नहीं पता चलेगा. So that's the only drawback. But other than that, if you give mock tests and worry about the absolute scores, yes, you can crack it. But you need lot of self motivation. हो सकता है. Think about the contributions, whether they add or subtract. Yes. Think about the contributions, whether they add or subtract. I feel, look at the circle. Okay, the circle is like this. Okay, so curl your fingers in the direction of that current flowing in that circle, clockwise. You will see the thumb goes inside. So the magnetic field is inside because of that circle, and it will be given by mu naught I by 2a, right? 2r. R is a over here. Everybody gets this? Great. Now think about the contribution because of the straight wire. This is as good as an infinitely long wire. This is infinitely long wire, and you are not on the axis, you are somewhere here. This is my distance. This is my distance. Chalo, where is the current going? The current is going towards your right side. Current is going towards the right side. Acha, so hold your thumb in the right side, okay, towards the right side. Ab dekho, how are your fingers curling? The fingers are curling like this. The fingers are curling like this. So matlab, when you are here, the magnetic field is coming towards you. The magnetic field is coming towards you. If you hold a pen or any pencil or any object, long object, you will see the magnetic field lines are coming towards you. तो उसका फॉर्मूला क्या है? म्यू नॉट I by 2 pi r. 2 pi r होता था. 4 pi r is when you put sin alpha and sin beta, but sin 90 will cancel and you will get 2 pi r. Yes, and hence the final answer, please understand, एक क्रॉस है, एक डॉट है, so subtract करना पड़ेगा. Which one of them? Yes, option B, guys. Option B. You can see that there is a minus sign. Why is this minus sign there? Because they are opposite. They are opposite. Is that clear? Everybody clear about this? Excellent. Lot of you got it wrong before this. Some of you had said A and D, but it's okay. You understood what mistake you did. 4 तो नहीं आया. Yep. Yeah. Why not D? Because it is not D. I mean, because look at this, there is a 4 here, there is a 2 here. देख लो यहाँ पर 2 2 है. So when you take out common, what will you get common? Mu naught I by 2a. Mu naught I by 2a will be common. 4 नहीं आएगा. Yep. I hope this is fine. Great. चलो. Okay. So that's option B, I guess. Yeah. Now let's see another question. This is also a beautiful question. Let's see how many of you get this right. So now there is a battery connected to a circular loop, and 1/4 of the part is here. Okay, 1/4 of the part is here, and the 3/4 part is here. ये quarter है, ये 3 quarters है. So the current will come in, it will get distributed, and it will again merge here and come back into the battery. So splits, comes back and goes here. So that's what is happening. Question is, what is the magnetic field at O? Come on, come on. Sunil, there is already a JEE Advanced free batch in Vedantu. It's called as Ekalavya. So you can join Ekalavya Sunil Kumar, है ना? और वहाँ पर फ्री एडमिशन हो जाता है फॉर पीपल अबाउट 97 परसेंटाइल एंड ऑल. और अगर आपका परसेंटाइल 96 97 से कम है, सो मुझे ऐसा लगता है कि यू गाइस शुड फर्स्ट फोकस ऑन जेईई मेंस. रीजन इज, अंडरस्टैंड, तुम्हें कोई भी एनआईटी, ट्रिपल आईटी या एक प्रॉपर गुड कॉलेज जो है एट 97 परसेंटाइल से नीचे या 96 से नीचे नहीं मिलता है. सो अनलेस एंड अंटिल यू हैव अ श्योर शॉट सीट in some NIT or some triple IT or some college which is centrally funded, तब तक तुम अगर JEE एडवांस की तैयारी करते हो, ठीक है, then most likely it is going to backfire. कहीं सारे स्टूडेंट्स में देखता हूं हर साल जो एडवांस की तैयारी कर लेते हैं 92 परसेंटाइल या 85 परसेंटाइल या इवन 91 परसेंटाइल और इवन 95 परसेंटाइल, और होता ये उनका JEE में रैंक भी आता है 20,000, और फिर JEE मेंस में अगेन सेम स्टोरी 95-96 परसेंटाइल. उनको ना ही आईआईटी का सीट मिलता है, दे डोंट इवन गेट अ सीट इन एनआईटी. हुआ क्या? कुछ नहीं मिला. एडवांस का रैंक आया. लुक एट द सिचुएशन. एडवांस, दे गॉट अ रैंक इन एडवांस, दे गॉट अ रैंक, दे क्वालिफाइड जेईई मेंस 96 परसेंटाइल एंड दे आल्सो गॉट अ रैंक, बट स्टिल दे डोंट हैव अ कॉलेज. ये सिचुएशन इज वेरी डेंजरस. So इसीलिए always make sure you apply strategy, get a seat, confirm a seat, and then move ahead. So unless and until you are about 96, 97, do not fully focus on JEE Advanced. Okay? Sunil, अगर तुम्हारा 98.28 percentile है, please join the Eklavya batch. It's free of cost. Teachers are amazing, and there are batches even running now. You can contact me on my Instagram handle, which is Shreyas_Vedantu. Yeah, just contact me on Shreyas_Vedantu. I will tell you how to exactly get into the free batch. Okay? Yep. Okay. Now, I'll tell you what. सबसे पहले understand the resistance of this path and this path is different. This is quarter of a circle. That means अगर इसका resistance R है, then the three quarters which is there here, that will have 3R resistance 3 times, because remember resistance is proportional to length. Resistance is proportional to length. Correct. Ab, what is current proportional to? Because the current gets divided, parallel में जा रहा है, that means the current is inversely proportional to resistance. तो अगर यहाँ पर understand, so if you see that the current over here is I, then the current over here will be 3I, inversely proportional. Wherever it is 1:3, it will become 3:1. That's what will happen. Exactly. Now let's do the question. What is the contribution because of the green part? So magnetic field because of the green part, the fingers curl like that. It is inside. So I'll just put across. And the formula will be mu naught. Current is I divided by, a radius which is A, so 2A. But it is 3/4 of a circle, so do not forget to multiply it by 3/4. Yes, do not forget to multiply it by 3/4. I hope this is clear. Similarly, figure out what is the magnetic field because of this 1/4 quarter of a circle part. The current is going this way, thumb comes towards you, that means the magnetic field is towards you. Next, what's the formula? Mu naught, current is 3I, okay, divided by 2. Radius is A, and how much part of the complete circle is it? It's 1/4 part, so do not forget to multiply it by 1/4. Don't you see both the terms are same? Don't you see both the terms are same? So what will happen? They will cancel each other and you will see the answer is 0. Yes, that's what will happen. Okay, I hope this is clear. Is this clear, everyone? Is this clear? Yep, very good. Good morning, Tarun. Welcome aboard. Very good. Okay, let's get going to the next question. Excellent. क्या बात है, कुछ लोग झारखंड से भी हैं. अच्छा, बहुत ही बढ़िया. Very good. चलो, next देखते हैं Ampere's law. Okay. Now, in Ampere's law, oops, I think एक मिनट थोड़ा पीछे चलते हैं. Okay. सबसे पहले ध्यान देना Ampere's law लगाते कैसे हैं. If you have some bunch of wires, okay, you have some bunch of wires like this, you can draw a path, closed path, let's say like this, which encloses some of these wires. This is just a path, hypothetical, it's there only in your mind, so it's nothing but a closed path. And these wires, both in, out, everywhere, will produce magnetic field. हर जगह पर there will be magnetic field. So let's say at this point the magnetic field is B. At this point, let's say it's something else. At this point, let's say it's something else. हर जगह पर there will be some magnetic field lines and magnetic field. What you need to do is go across that loop by covering small distances. Go across this loop, go a small distance dl. Then at this point you will have a different field. Again move some point ahead, again move some distance, again move some distance. Keep moving across the loop, and at every point what you need to do is take the dot product of B at that point and DL vector at that point. B DL, इस point का B, उस point का DL, उस point का DL, उस point का B, dot product लो, and then complete that loop, add them all. When you complete the loop, that's why you put this cyclic symbol to show कि आप पूरा loop गए हो. That's it. Integration means you are adding up all of these things. The answer will come out to be mu naught into I enclosed. I enclosed का मतलब है, you know, all the currents which are inside. These are the currents which are I enclosed. Keep this in mind. So the total current inside which are piercing through that path should be counted. The currents which are outside should not be counted. Keep this in mind. Yes. So this is from the top view. Okay. This was a nice 3D diagram which I draw. And you know, if you look at it from the top, you can see some currents are coming towards you, some currents are going inside, some currents are even outside that loop. Okay. So B dot DL ka integration, cyclic integration will give you mu naught I enclosed. Now mu naught I enclosed calculate karte waqt you need to be little bit careful which is positive, which is negative. Yes, this is like flux, but it is not called flux because flux is only when you take dot product with area. So electric field dot area, electric flux, magnetic field dot area, magnetic flux. So this is called as the line integral, not the flux. So electric field dot dr vector is the line integral of field, electric field. B dot dl is the line integral या path integral बोलते हैं इसको. Okay. Now if you go across this loop, ठीक है, like this, curl your fingers in the path in which you go. You are going like this. The thumb gives you the positive direction. So जो भी currents are this way are positive. All the currents opposite to your thumb are negative. So whenever you write mu naught enclosed, I enclosed, this will be according to sign convention. So curl your fingers. Thumb gives you the positive direction. ये current जो बाहर आ रहा है, okay, in the direction of thumb will be positive. जो current अंदर जा रहा है, that will be negative. That's how it works. Okay. So I hope this is clear, guys. So current has signs in Ampere's law. Just like if you remember in electric flux, when we used Gauss's law, okay, Gauss's law, cyclic integral E dot dA was Q in by epsilon naught. This Q in had plus minus signs because the charges had signs. Now that was very obvious. But in case of current, what happens is the direction needs that sign convention, and that sign convention is given by the right hand thumb rule. Okay, so keep that in mind. Now, using this Ampere's law, you can get the formula for magnetic field due to long solenoid, and I'll give you a bonus formula, and that is for a short solenoid. Very, very important. If you have a solenoid is nothing but you take a coil and wind it. Okay, wind it on a cylinder. So that becomes a solenoid, and you will see उसके कारण जो magnetic field बनता है. All you need to do is take your right hand. सब लोग अपना right hand लो. Just curl your fingers like this. You will see that the magnetic field will be in this direction. Yes, just curl your fingers. जिस direction में current जा रहा, उसी direction में you will see the magnetic field lines. And it will behave like a magnet. That's all. It will just behave like a magnet. Okay. Now, if it's a long solenoid, the field inside will be constant and it is uniform. Okay. It is constant and it is uniform. It's a long solenoid. And the field outside will be negligible. This is very important. It's almost zero. Yep. So the formula for the field inside is mu naught Ni, and the formula for the field outside is zero. It's negligible, neglected. This is very important. This formula is when you are inside. It is uniform. It is uniform inside. Keep this in mind. Yes, keep this in mind. Okay. Now, what is the meaning of this term N? This N that you see, what is it? Turns per unit length. काफी लोग इसको भूल जाते हैं. People remember it as number of turns. That is wrong. Small n is number of turns per unit length. ये याद रखो. Okay, that's one thing. Now, once this is done, okay, once this is done, let me give you that special formula, and this is that special formula for a short solenoid. Mu naught Ni by 2 sine alpha plus sine beta. What do I mean by short solenoid? See, the meaning of short solenoid is nothing but, if I take the cross section, ये आपका solenoid है, this is the cross section, you are here, okay, you are over here. You want to know what's the field over here. क्या करना है? Just draw a line till the end and again draw a line till the other end, and then draw a perpendicular on the solenoid. Yes, just draw a perpendicular. This is alpha, this is beta. This reminds me of straight wire formula. Exactly. This reminds me of straight wire का formula. तो ये side पे it is alpha, this side it is beta, or whichever you want, and that's it. Just use this formula. Mu naught Ni by 2 sine alpha plus sine beta. Guess what? It also works for long solenoid. How? Just think about it. If it's a long solenoid, okay, if it's a long solenoid, then the value of alpha and beta both will be 90 degrees. Both will be 90 degrees. Sine 90 and sine 90, 1 plus 1 is 2. 2 and 2 cancel. Mu naught Ni. Exactly same formula आ जाता है. This is very, very important. Yes, this is one shot marathon. Yep, this is one shot marathon. Okay, chalo, let's get going to the next thing. Yep. Application of Ampere's law में next geometry है toroids. Now what is a toroid? Toroid is nothing but a solenoid, but you turn it around and connect the ends. That's it. See, solenoid was like this. Solenoid was on a cylinder. You wind the turns. Imagine you bend that solenoid. You bend that solenoid. And then finally connect it, it becomes a toroid. That's it. That's a toroid. Now remember, I just told you, outside a solenoid, the field is 0. Only inside, the field is mu naught Ni. Only inside. It is, okay, inside it is mu naught Ni. Now obviously the formula for field should remain the same even for a toroid, because it's nothing but at the end of the day, a solenoid only. So toroid may be outside the field will be 0. It's nothing but a solenoid. Inside the field will be mu naught Ni only. कुछ अलग नहीं है. Don't remember separate formulas. Next up is mu naught. ध्यान से देखो अभी. कभी-कभी, you will see that instead of giving small n, they will give you total number of turns. They'll give you total number of turns. So replace this n with n divided by the total length of the toroid. The total length. Because remember, if you open it up, it will become a long solenoid. So total turns per unit length. So the length will be the circumference. Circumference is 2 pi r. So that becomes the formula for toroid. Keep this in mind. So there is no separate formula for toroid. It's solenoid formula only, just modified. Nothing else. Okay, let me just show that to you. Yep. Outside the field is 0. Okay, this should have been mu naught, guys. This should have been mu naught. Okay, cool. Yep. Why outside the magnetic field is 0? The reason is, you can see, when you have a solenoid or toroid, most of the field lines, okay, all the field lines will pass here, but when they go outside, they get distributed over a very large space. So do you see the density of field is very less outside? Hence the field outside is 0. Okay, Karthik? Very good, very good. Wow, Sanjana, very good. You have cleared VIT exam. Now please focus, bacha, on JEE mains examination. Please do that. My God, Sarvesh, either you are blind, or you are illiterate, or you are probably, I don't know, you don't know how to use computer. Okay, let's just bust this guy Sarvesh out. Let's just, do one thing. Let's just open up VNthus. Okay. I'll just tell you, I'll just prove what kind of people, what kind of idiots come to YouTube. Okay, these are the kind of idiots who come to YouTube. Okay, let's just go to past videos. Okay, there we go. Now, I don't know whether you can see this. This was me 21 hours ago. That was yesterday. Sunday. It is a non-working day, but I came on the channel on Sunday. Yep, I came on the channel on Sunday. And at the start of the lecture, and in fact before that, I mentioned very clearly that my microphone, this is a new microphone guys, I had ordered from Amazon. My old microphone, it's not working anymore. And I can show that to you. Yeah, let's just show these bunch of idiots. Yeah, this is my old microphone. It's still kept here. I'm going to return this. Yeah, this microphone is no longer working. Yep, I had to return this back because, yep, it stopped working. And before that, well, I conducted another lecture on Saturday. That's my life at NIT. Yeah, that's Saturday, by the way. Okay. Then before that, 4 days ago, that's 1D kinematics, I conducted it. Okay. And I mentioned it during the class that my microphone is not working. So for the next 2 days or so, till my microphone arrives, I will be unable to conduct the classes. So I don't know. I just missed 1 or 2 days. And this is the kind of feedback I get. I'm really hurt about this. Next one is a sheet. Now this formula is very, very special. Very few times you might get this kind of a problem, but if you get this, very few people actually know how to solve this. Let me tell you what this means. Imagine a sheet which carries current, okay, in a particular direction. Now in this case, you can see the wires are aligned like this. There are a lot of wires. Each one of them is carrying some current and they are closely packed. It's a bunch of closely packed wires which forms a sheet, infinitely long every side. Yep. Now, remember, if you just had a single wire, okay, it produces a magnetic field around it in the form of a circle. There is a circular magnetic field around it. But what if you have more wires around it? What if you have more wires carrying current around it? Then the magnetic field is no longer circular. Yes, what you need to do is use this trick. Very simple guys, very simple. Take any one wire, just take any one wire. Let's say I take this wire. Okay, let's say I take this wire. Let's say for the particular situation, let's say the current is going this way, that way, okay, in that direction. Just imagine it like to be a single wire. Hold it in the direction, hold your thumb in the direction of the current and see how your fingers are curling. Just see how your fingers are curling, okay. On the top it's going this way. At the bottom it's going this way. Just check this out. Just visualize this in 3D. Hold your thumb in the direction of current. See how the fingers are curling. On the top it's going towards the right side. At the bottom it's going towards the left side. I hope this is clear. That's it. Once you get that, remember one thing. On the top, everywhere the field will be uniform. It creates uniform field everywhere. Yes, and at the bottom, it's towards the left side. As simple as that. As simple as that. Nothing else. Okay. Now, do you remember, due to a sheet which is charged, it produces electric field which is given by sigma by 2 epsilon naught. That was the formula. Now over here, this sigma is replaced by lambda. Sigma is replaced by lambda. Epsilon naught was below. It will be replaced by mu naught on the top. You can see mu naught is on the top and that by 2 is still there. What is this lambda? This lambda is nothing but the current per unit length. It's very similar, the formula. Instead of sigma, which was charge density per unit area, it's current per unit length. So if I take 1 meter of that sheet, then how much current amperes is flowing in that? Because there will be some bunch of wires in that 1 meter. What is the total current per unit meter? That's the meaning of lambda. Just keep that in mind. Yeah. So it's not Q by L, it's current per unit length. That's the only change. Okay, so that's how I remember this formula, and that's how magnetism works. It's always opposite to electrostatics. If epsilon naught is below, mu naught will come on the top. If epsilon naught is on the top, mu naught will come below. If it's integration with length, it will be with area in magnetism. If it is charge density over here, it will be linear current over here. That's how it works. So if you remember electrostatics formula, you automatically will have some slight idea or hint about the magnetic formula as well. Okay, cool. Shall we go ahead? Now that you know the directions and the magnitude, here is the next question, next set of questions. Come on guys, let's see how many of you can do this. Beautiful set of questions coming up right now. The ratio of magnetic induction on the axis of a long straight current carrying solenoid at a point on the end to that at the center of the solenoid is. Let's see. Okay, well, guess what? This is a long solenoid. When you are here, okay, this is a long solenoid. When you are here, that angles, remember I had told you about those angles which are subtended. Each of those angles will be 90 degrees when you are inside a long solenoid. Remember, this is a very long solenoid. So both the ends will subtend 90 degrees. So what will be the formula? Mu naught Ni divided by 2, okay, into sine 90 plus sine 90. That means it will be just mu naught Ni, which is obvious, and that was the answer for inside formula. But when you are here, then one of the angle is 0, the other angle is 90 degrees. So it's 0 degree and 90 degrees. So hence the formula here will be mu naught Ni by 2 sine 0 plus sine 90 degrees. That's it. Sine 0 is 0, sine 90 is 1. So it will become mu naught Ni divided by 2. Mu naught Ni divided by 2. So can you see the ratio? Is it 2:1 or 1:2? Now don't make a confusion there. If you get that wrong, you will feel very bad about it. So it's a long straight wire, okay, fine, at a point on the end and at the center. At the end to the center. At the end it is half, the center it is 1. So it should be 1:2. Yes, correct. Option C. Option C. Beautiful. A lot of you got it. So a lot of people forget how to get to this, and remember the answer is using the short solenoid formula. Let's see how many of you can do this question. Beautiful question again, based on sheets. Based on sheets. Felix, I think you made a mistake. Yeah, 1:2. End is to center. That was the scenario. So end was half, mu naught Ni by 2. Center was just 1, mu naught Ni. Now, there are two sheets. Sheet 1 here, sheet 2 here. Sheet 1 has lambda current density. Sheet 2 has 2 lambda current density. This sheet carries current this way. This sheet also carries current this way. It's like two parallel sheets. Both the sheets have currents coming towards you. Now, we need to figure out what's the current here, what's the field here, here and here. 3 regions. There are 2 plates, region here, region in between and region below. These 3 regions, what is the field? Let's do this. First, let's take this lambda. Current is coming towards you. So imagine holding some object, pointed object, and make sure the current is coming towards you, and hold your right hand thumb like this. Hold your right hand thumb in the direction of current. You will see the fingers will curl this way. That means on the top, the field is this way. Okay, on the top, the field is this way. And if you go below, you can see below, the field is that way. Remember, uniform field is produced. So the field here will be in this direction because of this sheet. Because of this sheet. And what's the formula for this? Mu naught lambda divided by 2. That's the formula. Correct? That's done. Now for the second sheet. For the second sheet, what will you get? 2 lambda is here. 2 lambda current is coming towards you. Again, hold the thumb in the direction of current. You will see the fingers will curl like this. On the top, it's towards your left side. So above this sheet, the field is here, and below the sheet, the field is here. And what's the magnitude of that field? It's mu naught. Oh, the current density is 2 lambda divided by 2. That means mu naught lambda. Cool. Now the only thing left is finding out magnetic field in region 1, magnetic field in region 2, and magnetic field in region 3. Only these 3 things are left. Remember, each sheet will contribute its own magnetic field. Now what you will see in region 1, both these fields are adding. Yes, they are adding. So mu naught lambda by 2 plus mu naught lambda, that means 3 by 2 mu naught lambda towards this side. That's in region 1. In region 2 they subtract. So it will be mu naught lambda minus mu naught mu naught lambda by 2, which is mu naught lambda by 2 again. But what direction? Red one is smaller, blue one is bigger because it is mu naught lambda. So it should be in this direction. You can see that. Last thing over here is that the third region, again they add, and obviously you should get 3 by 2 mu naught lambda, but this time in that direction because both the arrow marks, both the vectors are in this way. So that's how you get the magnetic field in these 3 regions. Yes, the directions are also important. They can ask you the directions. This is a very good question if it comes in mains or even in NEET. Okay, chalo, bahut hi badhiya. Let's get going to the next question coming up on your screen now. Yeah. So current I flows along the length of an infinitely long, straight, thin-walled pipe. Then only one of them is correct. Only one of them is correct. Think about it, which one is correct? Okay, so this is your pipe and it is infinitely long. So the wires are parallel like this. Okay, it goes like this. Yeah. Now, if I take any Amperian loop, what is this? This is a closed path. If you take any closed path inside, the cyclic integral B dot dl will be mu naught I enclosed. How much current is enclosed inside this loop? There is nothing cutting through it. There is nothing at all. Guys, yes, this itself is 0. That means if I take any integral, this is for any path inside that particular pipe, remember it was a pipe, everywhere the value of the integral will be 0. That can mean only one thing, the value of B itself is 0. The value of B itself is 0. So the magnetic field at any point inside the pipe is actually 0. Any path, no matter which path you can take some other path over here like this. Okay, even that path will have 0 as the value of the integration because there is no current enclosed inside. Everything is going outside that loop. So hence the answer is option D. Keep that in mind. All right, let's get going to the next one. Yes, the correct answer is D. Yeah, a lot of people get confused over here. Let's get going to the next set of problems. But before that, I hope you remember the force acting on a charged particle which is thrown inside a magnetic field. So if you take a charged particle, something like this, and let's say you throw it over here with velocity v, it will experience a force due to the field which is given by q v cross b. So if v is there, b is inside, v is there, b is inside. If you do v cross b, you will see my thumb pointing this way. V, right hand fingers, cross B. You'll see the force acting this way. So the force will be in this direction. Yep, the force will be in this direction. So that's the answer. And you should remember this formula. Let's see some questions based on that. But before that, let me also tell you some more things that, you know, if you throw, look at this point. If you throw the charge in the direction of the field, the force will be 0 because the cross product will be 0. Understand that. So force acting on a charge which is moving parallel or anti-parallel, remember the cross product will be 0. So no force at all, it will continue moving in a straight line. Nothing will happen to it. Now these are the two important cases which you should know. Yes, it is a 2-hour session. Oh my god, Shreyas, that's why I said please get your food and water around you, so that you guys, if you feel dehydrated or if you feel hungry, please munch on the snacks around you. Yes, please do that. Okay. If you throw a charge perpendicular to the magnetic field, if you throw a charge perpendicular to the magnetic field, it will go in a uniform circular motion. This is a standard case which you should know. Uniform circular motion. The magnitude of the velocity will be constant. You should know the formula for radius also. Radius is mv by qb. That's a standard formula which you should know. It comes by the centripetal force. It's provided by the magnetic force. And if you just write magnetic force is qvb and centripetal force is nothing but mv square by r, from this you will get that. You can get more things from this as well, like the time period and all that. Now this is when the velocity is perpendicular to the magnetic field. There is another situation when the velocity is not perpendicular or parallel but makes an angle, let's say theta, with the magnetic field. In those scenarios, split the velocity into two components, v sine theta and v cos theta. Now think about it, which of these two components will be unaffected by the magnetic field? Yes, correct, Karthik. V cos theta will not be affected, it will be constant because the force will be zero. Remember, when velocity is parallel or anti-parallel to field, the force is zero. So hence you will see this component will not be affected. Whereas this component, this one, use this logic. When the velocity is perpendicular, what will happen? It will go in a circular path. It will just go in a circular path. So that's all that happens in this scenario when velocity is at an angle. One component will ensure it goes in a circular path. The other component will make sure that it goes uniformly in one particular direction. So one component makes it go in a circle, other component makes it go in a uniform path. So if you combine both of them together, you get the helical path out here. Yes, you get the helical path out here. So you will see that the particle continues like this. It continues circular motion and keeps moving ahead in the direction of the field. The distance between these two lines is called as the pitch. So what is the pitch? Is the distance between these two lines. You should know that. Yes, you should know that. And the radius, yes, the radius of that helix will be given by the same formula, just that instead of v, you will use v sine theta. That's it. The radius of the helix, okay, instead of that v, you will use v sine theta because that's the component which is perpendicular to the field. Keep that in mind. Yes. How is force zero? Because v cos theta and b are parallel. So v cos theta is parallel to b vector. So that's the reason why the force is zero. Remember, it's a cross product. That's why. Okay, cool. So keep all these things in mind. Cool. Let's get going. Let's get going. Okay. By the way, I have put up all the theory out here for you guys so that when you get the PDF, you can go through these theory points and you can also revise through all these things. Okay, let's start with some questions. Okay, no problem, Clay Tsunami. A deuteron of kinetic energy 50 kilo electron volt is describing a circular orbit of 0.5 meters in a plane which is perpendicular to the magnetic field. The kinetic energy of the proton that describes a similar circular orbit of radius 0.5 meters in the same plane with the same field is, radius is same, energy is different, field is same. Okay, let's see what and all. R is same, B is same, charge, deuteron and proton, they will have the same charge. So Q, all of these quantities are same. And do I know the formula for radius? Yes, it is mv by qb. mv is nothing but momentum. So it's nothing but momentum divided by qb. And momentum is nothing but 2 root of 2 mk, where k is the kinetic energy, m is the mass. Everybody knows how to relate these two. Okay, so that's the formula between momentum and kinetic energy. Now square both the sides and rearrange. you will get K is equal to R square, Q taken up squared, B taken up squared, and 2m taken below, so 2m downstairs. That's the formula for kinetic energy. Now R is same, m is different, Q is same, B is also same. Therefore, the kinetic energy of that particular proton upon kinetic energy of deuteron, it's only inversely related to the masses. You can clearly see that. So it will be mass of deuteron upon mass of proton. Mass of deuteron is twice of that of proton. It's 2 times, 1 proton, 1 neutron, that's deuteron. And Kp divided by K of deuteron, that's given, it's 50. So naturally Kp will be 100 kilo electron volt. That's the answer. Yep, very good, very good, very good. Yes, that's the answer. Where is it? Yep, here, 100 kilo electron volt. Very good. So all you need to do is use the formulas, guys. I mean, you will get it. Cool. Let's get going to the next question coming up on your screen. Okay, answer D. Let's see how many of you get this. An electron is projected with uniform velocity along the axis of a current carrying long solenoid. Which of the following is true? Only one of them is true. You're throwing a particle, charged particle, along the axis of a long solenoid. Think about it. Only one of them is true. Wow, very good, Daditya. This similar question came in your JEE shift. Kya baat hai? Okay, so I'm pretty sure you know the answer. People are saying B. Oh my God, people are saying B. No, no, no. Guys, the answer is D. The electron will continue to move with uniform velocity along the axis of solenoid. Please keep that in mind. Why? Because this is your solenoid, okay? This is your solenoid. How will the magnetic field be? The magnetic field will look like this. This is the magnetic field because of that solenoid. How have you projected it? You have projected it like this. Projected with uniform velocity along the axis. This is the axis, guys. This is the axis of the solenoid. What will be V cross B? V cross B will be 0. Force will be 0. If force is 0, what will happen? It will move with uniform velocity. That's it. Yep. Oh my God, Aditya, you still got it wrong. That's bad. Please read it. It's a solenoid. It's clearly mentioned. My God, no wonder it came in JEE Mains. Looks like people have the habit of missing words. Venkata, can I? Okay, meanwhile, guys, start solving the next question coming up on your screen. I'll just look at Venkata's query. Can I solve NCERT without reading? It's whether it's okay or I want to read. Venkata, if you have understood the concept from H.C. Verma or whatever book you are following for theory, after that you should read NCERT no matter what. You should go through all the theory pointers, all the important things. For JEE Mains, NCERT is very, very important. There are a lot of questions, theory points which come directly from NCERT, solved examples, even back exercises as well. Let's see how to do this. There are two charges go in identical helical paths but in opposite sense. That means one particle goes like this and the other particle goes like this. The only thing which is different is, think about it, oh by the way, this should be your z-axis, this is your b vector in b naught k cap, that's the magnitude and the direction. Okay, so it says they have equal z components of momentum. This is wrong. They do not have equal components because directions are opposite and momentum is a vector quantity. So two vectors are equal only if magnitudes and direction are same. So option A is wrong. Understand that. Yep. So I hope this is clear. So this is in z direction. Okay. They must have equal charges. That is also wrong. The charges must be opposite in nature. Yes, they must be opposite. If one is plus, other should be minus. That's why they are going opposite. They necessarily represent particle anti-particle pair. No, it could be some two particles, same mass, same magnitude of charge, but opposite signs. So necessarily, no, it's not necessary. This option is correct. I'll tell you how. Because, you know, even if you just write the formula for radius, radius of particle 1 and radius of particle 2 magnitude wise is same. So the radius of particle 1 will be, m1v by q1b, and radius of particle 2 will be m2v by q2b. Now v, b gets cancelled, and this is only magnitude wise. Keep this in mind, one of the charges is negative. So strictly speaking, it will be m1 by q1 if it is E. So it will be m2 by minus E. The charges are, opposite in sign. So when you take this on the other side, you will get this. So you will get this from here. Yes, these kind of questions are asked in JEE. So these are those typical 5-10% of questions, Jagdish, which are meant to separate out the average crowd from the toppers. Not everyone will do this. For an average student who wants to get 90 percentile or even 92 percentile, I will tell, ignore this question because it's quite conceptual. But for people who want to score above 92, 93 percentile and want to be in the top league, you have to solve these kind of questions. Yeah. So understand that. Okay, chalo, let's get going to the next one. Okay, now this is very important theory, crossed field. If you throw a particle, with some velocity in electric and magnetic field such that it does not get deflected, no deflection, then there is only one way this is possible: if velocity is perpendicular to electric field and it is also perpendicular to magnetic field. Look at that, electric field here, magnetic field inside, velocity is here. All three are mutually perpendicular to each other. Yes, all three are mutually perpendicular to each other, and you will see why is it going without any deflection, because the electric field will apply a force like this in the direction of the field. Magnetic field will apply a force in the direction of V cross B. V is there, B is here, thumb is up. So V cross B is here. So that's the force of the magnetic field. If these two forces are equal and opposite, they will cancel. You will see the net force is 0 and it will go without any deflection. Yes, it will go without any deflection. And when you equate the forces, you will get this. V is equal to E by B. This is something you should remember. Speed is E by B. Only when this ratio is satisfied, it will go in a straight line. If it is not satisfied, if one of them is more or less, it will get deflected here or it will get deflected down. Keep this in mind. Yes, JSK, this is a one-shot marathon lecture. Understand that. Yes, this is one-shot marathon lecture. So guys, for all of you who are studying for 2021 or 2022, understand on VNThu's channel. This is VNThu's channel. We take regular classes, and if you just go to playlists out here, you will see all the playlists. Like there is a JEE Preparation playlist. There is a JEE Maths playlist taken by Shimon Sir. Then you have JEE Physics playlist, that's by me. JEE Chemistry playlist by Wazim Sir. So like just to show you an example, you can see in this playlist there are all kinds of series out here. These are rank booster series for 12th standard students and passing out students. These are strategy sessions. This is 0 to Hero series, which is again for 12th and passing out students. Rapid revision series. This is long-term batch. This is long-term batch for 12th standard, and this is long-term batch for 11th standard students. All of these series are there, and then if you want it chapter wise, all the chapters are also arranged, whichever chapter you want. Most of the chapters are there. Okay, you can see that out here. So that's how it goes. Okay, cool. Good morning, Pragya X Gallery. Welcome. Okay, let's get going with some questions. But before that, for the force on a current carrying wire, remember, just like you have a force on a charge, a current carrying wire is nothing but many charges moving in it. So even a current carrying wire will experience force, and that formula is given by IL cross B. I is the current, L is the length, and B is the magnetic field. IL cross B. Remember the direction of L, the direction of the length of that wire is same as the direction of the current. Yes, So if this is a wire carrying current, make sure your length vector is in that direction and then perform L cross B so that you get the force. Please do not use your left hand rule, right hand rule, and then mark this is F, this is I, this is B. Then in electromagnetism, you will forget which one was what for BLV. So do not do that. It's very confusing. Just always stick to your right hand thumb rule. That's it. That will always give you the answer. It's very easy if you know vectors. Okay. Now, this is a very important property. The force on a curved wire is always the same as a straight wire. That means if you have a curved wire carrying some current and it's placed in some magnetic field, to find the force, what you do is forget that wire, just join the endpoints. Whatever force acts on the curved wire will be the same force that acts on a straight wire. That's very easy. Yep, remember that. So force on a curved wire is the same as the force on a straight wire, connecting those ends carrying the same current, obviously. Okay, keep this property in mind. Okay, let's do this questions. And the last property, obviously this makes sense. I mean, like if you have a loop, the net force will be 0. Why? Because imagine if you have a loop, what's the start and what's the end is the same, right? So what will you replace it with? For a curved wire, you used to replace the start and end with a straight wire. But here, the start and the end are same. So the effective length will be 0, and hence the force on it is also 0. Keep this in mind. Yes, the force on it is also 0. Let's also go ahead to the next part. Yep. If two wires are in the same direction, they will exert forces on each other, and that force, because they are same direction, it's very opposite to electrostatics. Like charges repel, but in magnetism, like currents will attract each other. You should remember this. Like currents will attract each other. But if you have currents in the opposite direction, then yes, they are going to repel each other. Keep that in mind. Yeah. So it's opposite to that of electrostatics. In electrostatics, opposites attract, similar things repel. In magnetism, similar things attract, opposites repel. Understand that. That's the logic. And the formula for attraction or repulsion, you should know that. Force per unit length. Very, very important formula. This is force per unit length. Now, force per unit length is given by mu naught I1 I2 by 2 pi d. What is d? D is the distance between them. Okay, d is the distance between them. Okay, that's it. That's what you should remember. Shall we do some questions now? Okay, I hope you have noted down all these formulas, and plus somebody is there to revise these formulas for you. It helps a lot. If you had to just read it on your own, probably you would never do that. What is L? L is force per unit length. L is length. Yep. L is length, not current. Okay, be careful. This is I1, this is I2, let's say. This is I1 and this is I2. Yep, great. Chalo, let's solve some questions out there. Coming up on your screen. First one is little bit easy, I guess. Let's see how many of you get this. I'm going to give you only 20-30 seconds. Figure this out. It's not that lengthy question. Two wires carrying current, okay, in the same direction, A and B. X and Y are two electron beams moving in the same direction as shown. Okay, read the questions carefully. Then there will be X and Y are electron beams, A and B are current carrying wires. Okay, first let's talk about A and B. Yep, let's talk about A and B. A and B, okay, for A and B, the direction of current is same. What did I say? Whenever the direction of current is same, similar things will attract. So same means it should attract. Great. So this is how the currents were going. So obviously they should attract each other. So attraction between A and B. So obviously A option is gone and even C option is gone. Yes, A and C is gone. Done. Now between B and D you have to choose. See guys, if electrons, what is electron? Negative charge goes towards this side, it's as good as saying the current is going this way. The current due to them. Because electrons are negative charges, it's as good as saying positive charges are going towards the left side. Now, X and Y, again same direction, so they will again attract. Obviously, they will attract each other. But if I ask you, what about this current and what about this current? These two are opposite, and when they are opposite, what will they do? They will repel each other. So there should be repulsion between X. Oh, wait a minute, sorry. Repulsion between X and Y? No. And also between X and Y? Yes. So X and Y will also attract. Yep. I hope this is clear. But there is a problem. Lot of you are going to mark this D option. Correct? But guess what? This question has a big catch in it. Do you know what? It is? Yeah, very good, Dhruv. Okay. There is a small catch over here. Yes, it's not so simple. Lot of you might think that just because electrons or whatever charges move in this direction, it's as good as saying current is in this direction. Yes, I agree to that, no doubt. But there is a problem. The problem is that Ampere's law or the magnetic field formula, etc., okay, whatever you apply, B dot dl, okay, mu naught I enclosed, whatever formulas you apply, this is valid. This current is when you have a conductor full of nuclei, which is positive charges, and there are electrons or negative charges moving in the opposite direction. When you have stationary positive charges and electrons moving in the other direction. That's what this current I means. This current I stands for positive charges at rest, electrons moving in the other side. That is calculated as the current. But just charges moving without any other stationary charges is not counted as current in the Ampere's law. That's the problem. Yes, that's when things go wrong, and there are some relativity effects which take into which happen or which needs to be considered, and things behave very differently. Yes, let's not worry about that. Just think of it this way, guys. X and Y are negative charges, right? This is also negative charges moving this way. Let's say you are on those negative charges. You sit on those negative charges. You just sit on that. What will you see? There should be electrostatic. There should be electrostatic repulsion. Yes, there should be electrostatic repulsion. So these negative charges should repel. These negative charges should repel according to the law of electrostatics. If you think about it, yeah, negative charges, yes, they should repel. So these two electron beams should actually end up repelling each other and not attracting each other. That's the catch. So current carrying wires will attract, but charges flowing in the same direction, they will repel. So understand, there is a difference between a current carrying wire and just pure charges just flowing in one particular direction. Understand. So that's why the answer is B and not D. Lot of people think the answer is D. Yes. So Sakti, the thing is, you do not study relativity in JEE, so that's why we do not discuss that over here. But the point is, the law of electrostatics should still be valid if you find the charges at rest. And if you sit on those electrons, yes, the charges are at rest, so law of electrostatics is valid. So they should repel. So if they repel, from outside also they should repel. So that's why it should repel. Yes, understand that. You never know, Jane. You never know. What if they are asked? Yep. Got it? So that's the problem. Yeah, that's why the answer is B. Okay. Let's see how many of you get this question. Oh, you never know, Jane. Like there have been times when they have surprised the people by asking random questions. So you never know. Just, it's a food for thought. And it's important to know that current carrying wire and charges moving are different. That's all you need to know. Okay, just keep that in mind. Okay, now there is a loop which carries current. Okay, and the question is, what's the tension in that wire? Now you might be wondering, why the hell will there be any tension in this? Why the hell will there be any tension in this? The fact is, if you take any element over here, okay, let's say I take this element. Okay, this is DL. DL is there. Magnetic field is inside, you will see the force is upwards on this element. In fact, every element you will see will experience a force like this. Now because there is a force which is stretching it outwards, that's why there is a tension which is developed in the loop. So this force of outward pull creates that tension in that loop. It's like somebody is trying to pull it outwards. Now to figure that out, it's a very simple job. All I will do is just take a semicircular part. Yes, just take a semicircle. Okay. Now obviously on that semicircle there will be forces acting at every point due to IL cross B force. And we also have tension here and here, because I'm just taking half the part of that complete loop. Tension will be here. Remember, tension only acts along the string. That's why here and here. That's it. Now, the only thing missing is, I do not know what is the net force because of this. All these black ones are out here. People might think I need to integrate. No, there is no need of integration. All I need to do is replace this black wire with a straight wire. Because the force on a curved wire and a straight wire is the same. So whatever force acts on the straight wire is the same as the force which acts on the curved wire. And what is this force? I length 2r into B. That's it. Now for equilibrium, what will you say? I into 2r into B should be equal to T plus T. Right? T plus T should be equal to I 2r into B. So therefore T is equal to IRB. That's the answer, guys. Yes. 2 times. No. It's finally the answer is just IRB. That's the answer. Great. So we have used the property where a curved wire can be replaced by a straight wire. It simplifies the problem. It avoids the unnecessary step of integration. Yep. That's it. Correcto. Let's get going to the next one. Now a question which is very similar to the previous one, just one small thing has been added. Apart from that current carrying loop, you are also spinning that loop. Yes, you are spinning that loop. Then the tension in that loop will be 0, more than IRB, less than IRB, or does not depend on the rotation. Come on, think about it. You are spinning that loop additionally. So what do you think, guys, will happen? Okay. Yes, apart from that outward pull, there will be one more extra pull. Yes, and that's the centrifugal force. Correct. That's why it will be slightly more than IRB. Correct. Yeah, the centrifugal force is going to push it more towards the outside, and hence you will see the tension will slightly increase. Very good. So if you know that question, only then you can solve this question. Else you will be like, why is this IRB over here? Okay. Last few things are there. Let's go to magnetic dipole moment, the torque and the bar magnet theory quickly, and then we can start solving those questions. Magnetic dipole moment. If you have a loop carrying current I and the area is A, then it produces magnetic dipole moment the direction is given by right hand rule. Curl your fingers in the direction of current. The thumb gives you the direction of the dipole moment. And the formula is NIA, National Investigation Agency, NIA. Okay, so N is the number of turns, I is the current, A is the area enclosed. Unit you can clearly see it is amperes into meter square. Remember, the direction of the area vector or the magnetic moment vector is by the right hand rule as shown over here. It's a vector quantity, keep that in mind. Remember this formula, write it down. NIA is magnetic dipole moment or just magnetic moment. It's one and the same thing. Some books use the symbol capital mu. I think that leads to a lot of confusion. Okay, next up, if you take the same loop, or National Institute of Archaeology, yes, correct. Now if you take the same loop and put it in somebody else's magnetic field, okay, you put it into somebody else's magnetic field, that loop will rotate because it experiences a torque, and that torque is given by M cross B. M is that way, B is that way. It will create a torque and it will reorient the loop in the direction of the field. That's the torque experienced. And the formula, when you rotate it at different points, it has different relative potential energy. That formula is given by minus M dot vector B. So understand the previous one, magnitude of the torque is MB sine theta, but this one is minus MB cos theta. There is a minus sign and this is a dot, keep that in mind. That's how you should remember. Also remember one thing, when you have that loop which is carrying current, okay, so let's say this is the M vector. When that M vector and that field vector are perpendicular, cos 90 is 0, so that's when U is 0, and they are perpendicular. That's very important. Yes. So Jane, for a circular loop or for a square loop, doesn't matter. The direction of the area vector is always dependent on the direction of current. If you do not know the direction of current, then you have both the options. You can take it here or here. So in order to decide whether it is this or this, you need the direction of current. Without that current, you cannot do that. Okay, cool. Let's start solving some questions out here. There is a magnetic dipole free to rotate in uniform magnetic field. For what orientation of the dipole with respect to the magnetic field, the torque is maximum, potential energy is maximum. So for what theta, for a loop carrying current, do you think, the torque is maximum, potential energy is maximum? Figure this out. Yep, it should be C, guys. Because sine 90 is 1, cos 180 is minus 1. That's the reason for that. Torque is very simple because it is MB sine 90. That's okay, it's maximum. For potential energy, minus MB cos 180. Cos 180 is minus 1. So it will become plus MB. Plus is bigger than minus. If you put 0, 0 is obviously, cos 0 is 1. That negative sign will make it less. So it should be 180 degrees. That's the answer. Let's get going to the situation where you need this table, guys. I mean, like for getting a visualization to get the feel of how exactly a magnetic dipole behaves. Like you can see, if the magnetic dipole has 0 degrees, okay, it's in the direction of the field, then the torque is 0. Energy is minimum, minus MB. And if the magnetic dipole is perpendicular, you will see the torque is maximum. And if it is 180, you will see the torque is again 0 because sine 180 is 0. Same thing in potential energy, when it is 90 degrees, it is 0. When it is 100 and 180, it is plus MB, which is maximum. So 180 degrees, it's maximum energy. 0 degrees, it is minimum because it is negative MB. Keep this in mind. Yes, keep this in mind. Yes, can angular SHM be performed? Definitely, Jai Ajinkya. If you take this magnetic dipole, displace it slightly and leave it, you will see it will oscillate like this because the torque will keep restoring it back to its original position. It will oscillate. This kind of equilibrium is stable because you displacing this dipole here or here will restore it back. This is not any equilibrium because the torque is not zero. In fact, the torque is maximum. Only when the torque is zero, you can say that it is equilibrium. Understand that? Yes, that's how the compasses work, correct. Now, if you take that needle and flip it to the other side, this one, unstable, it will immediately flip back to the other side. So this kind of equilibrium where you rotate it by 180 degrees against the field, that's it. That's going to be an unstable equilibrium. Keep that in mind. So you should know that feel of how things will work for a magnetic dipole. Very important table for all of you. Let's do this question. Good question for all of you based on a lot of visualization. Read it. There is a square loop of side 2A and it carries some current. Okay, and it is kept in the XZ plane with its center at the origin. A long wire carrying some current is placed parallel to the Z axis and passing through some point on the Y axis. That point is very far. That's what it is written. B is much larger than A. So the question is basically, what's the magnitude of the torque on that loop about the Z axis? Best thing to do, draw the diagram. Without drawing the diagram, you will not get it. Yes, first draw the diagram. Okay, square loop, side 2A, carrying current I is kept in the XZ plane. So remember, this is X, this is Y, this is Z. Okay, the XZ plane with the center at its origin. Okay, so let me just draw somewhere here, maybe. Just draw it here. Okay, this is the square loop and this is the Y-axis, this is the X-axis and this is the Z-axis. Okay. Now, a long wire with the same current is placed parallel to Z, okay, passing through this point. Now, this point is obviously on the Y-axis. So that means you need a wire somewhere maybe like this. This is that wire parallel to the Z-axis and it carries the same current. Okay, that's what it is. Okay, cool. Now the question is, what will be the torque? It's crazy. Now visualize this first. This wire, if you look at it from this side, it will look like this, like a dot, and you will see that this square loop is somewhere below it and this is the Y-axis. This is the Y-axis. This loop is in the XZ plane. XZ plane. This current coming towards you will produce magnetic field around it. Correct? It will produce magnetic field around it. So the B over here is this way in the X-axis. This is along the X-axis. Keep this in mind. But the loop, since it carries some current, there is some current in that loop. Because of that current, it will produce a magnetic moment. Yes, use your right hand thumb rule and it will be like this. It will be like this or maybe like this. I don't know. But the point is that the magnetic moment is perpendicular even if you take it up or even if you take it down. That means the torque acting is MB sine 90 degrees. That's it. The torque is MB sine 90 degrees. And what is the value of M? Magnetic moment, NIA, is just one loop. So N is 1, I is I, A is side square. So 2A whole square. That's M. Now what is B? Magnetic field at some distance due to a long wire. What's the formula? Mu naught I by 2 pi distance. Distance is B. Yes, just put it out here. Which is the option that you are getting? Are you getting this one? Just check this out. If you get this one. That's how it is. Isn't it a beautiful, tricky visualization based questions? No diagrams given. Just via the text you have to guess what the answer is. Beautiful question, guys, it is. Yep. Option A. Very good. Beautiful. Great. Chalo. Let's get going to the next one. Okay. There is a square loop it carries some current, it has some magnetic moment. Now you remove that loop, convert it into a circle, same current. What's the new magnetic moment of the loop? Okay, chalo, let's see what we can do. First of all, if you have a square loop, okay, carrying some current, the magnetic moment is given to be M, and it is NIA. I don't know what's the side length, but let's just assume it to be A. Okay, so it will be A square because each side length is A. Okay, cool. Now, if you take that same wire and convert it into a circle, let's say that radius is R. Okay, now before going ahead, just remember the length or that perimeter is same. Yes, the length or that perimeter is same. So what is the perimeter of a square? Well, that's 4a. And what's the perimeter of a circle? That's 2 pi r. So therefore r will be equal to 2a divided by pi. Yes, that's the new radius of the circle. That's how I get it. Now use this radius over here to find the new magnetic moment. That will be n, I is the same, area is pi r square. So just substitute it. I into pi into r square, that's 4a square by pi square. So you can see that I and okay, I just have this a square also over here, ia square over here. One of the pi's will get cancelled and I'll just have 4 by pi. This one is nothing but, you can see, ia square is nothing but m. So it's 4m by pi. Where is 4m by pi? That's option D. Okay, very good, very good. A lot of you have answered that. Yes, a lot of you forget that you have to convert it into, you need to find the new radius because the length is constant. So that's where the common mistake is, or that's where the point most people get stuck. Very good. So perimeter is constant, that's all. Okay, let's get going to the next one. Beautiful question again. This is a shell which is rotating with angular speed omega. There is a charge q which is distributed uniformly on it. What's the magnetic moment of the sphere? What's the magnetic moment of the sphere? Let's see how many of you can do this. Now, remember one thing. There is one option where you take each point charge on the sphere and you see that it describes the circular path. So it's like current, and there will be many such loops because each charge on that sphere will go in a circle, different circle, and then you find magnetic moments for each charge, add them up, integrate it and get the answer. That's option number 1. But you are not going to do that. Don't do that. There is a simple formula which you should remember, and that is magnetic moment by angular momentum is charge divided by twice the mass. Magnetic moment by angular momentum is q by 2m. That's the formula. If you remember it, done. So m by L, let me just shift L on the other side. So m will be equal to, q is capital Q, mass is it given? No, it's not given. Okay, L when it's taken to the other side, well, angular momentum is I omega. Okay, it's I omega. But what's the value of I? It's a shell, right? It's given, it's a spherical shell. So it is 2 by 3 m r square. Now don't you see guys, m and m just got cancelled, and what is left? Oh, even this 2 will get cancelled. This 2 and this 2 will get cancelled, and you will be left with q r square by 3, and omega is also there, out there. That's it. Just check this out. Q r square omega by 3. Yep. Interesting, isn't it? You don't have to do any integration if you remember this formula which I have written down. So guys, remember, you can use this formula for any rotating rigid bodies. So any rotating rigid bodies, on the top you have magnetism, at the bottom you have rotation. Beautiful. So studies, here is the trick. Use m r cross v for point particles, for point. Use I omega for bodies like this, rigid bodies, for big bodies. Understand? That's how you do that. Yep. Is that clear, studies? Sir, by charge density and integration we can also find. Yes, Jay, but you don't have that much time in the examination, let me tell you that. It's not possible. Okay, so if you want to do, you can do it, but then you'll not be able to solve many other questions. Last thing for today, that's magnetic dipole moment and magnetic charge. So just quick revision of the formulas. A bar magnet consists of south and the north pole. The south pole has -m charge. This is the pole strength, that's small m, and plus m is the pole strength, even this one. Plus is used for north, minus is used for south. Okay, just like you have two kinds of electrical charges, you have two kinds of magnetic poles, plus m and minus m. The distance by which they are separated is called as the magnetic length. It's called as the magnetic length. Remember, in electricity, if you had plus q and minus q charges, and this was the length, you defined electric dipole moment as charge into the length. That's how you defined electric dipole moment. Same way, you will see the magnetic dipole moment is nothing but magnetic charge, which is m, into the separation, which is L. That's it. That's it. Yes, that's all. And remember, the direction of this L is always from south to north. South to north, not north to south. South to north. So the magnetic dipole moment in this case is this way. Keep that in mind. Yep, very, very important. Okay, so I have put this up in your slides so that you remember all of these things, and you also have it for revision. Okay, and just like you take a loop, okay, you take a loop and you place it in a magnetic field, it experiences torque. Even a bar magnet is nothing but very similar to a loop carrying current. This is your loop which produces this magnetic moment. This is a bar magnet which produces magnetic moment. So if a loop can experience torque and can have potential energy, even a bar magnet can experience torque and will have potential energy. That's all this says. So you can see the formulas are similar. In fact, it's the same. So just like you have formulas for torque and potential energy, you also have formulas in case of bar magnet, which is very, very similar. Exactly in electrostatics, current carrying loops, it's one and the same thing. There is no difference. So let's see how many of you can do this question. Very interesting question. A bar magnet of magnetic moment 5 ampere meter square is suspended in uniform field. Strength is 2 Tesla, making angle 60 degrees with the direction of the field. The potential energy of the magnet in that position is... Kavi, after 5 minutes the lecture is over. Okay, just last 5 minutes. Okay, and then we are done. Get this out. So you have a bar magnet, okay, and the magnetic moment is 5 ampere meter square, and it is put in a magnetic field of 2 Tesla, angle is 60 degrees. What is the potential energy? Just use the formula minus mb cos theta. What is m? 5. What is b? 2. What is cos, and the angle is 60. Cos 60 into 2? Half into 2, 1. So answer is -5. That's it. B option. Beautiful. Some of you said C. That's wrong. Answer is B. Okay. Sorry, some of you said D. My bad. Yeah. Okay. Correct. -5 joules. Let's see whether you can solve this question. Again, there is a magnet kept in a magnetic field. Initially, it is aligned with the field. You move it by 60 degrees. To move it by 60, you do a work of 24. Now you move it more by 60 degrees. How much work will you do for moving it further by more 60 degrees? Come on, let's figure this out. I'll give you a hint. The work done is change in the potential energy. Just use this fact, you will get it. I'll tell you what. Change in energy, right? Because whatever work you do goes in increasing or changing the potential energy. So earlier you were at 0, then you move to 60 degrees. So potential at 60 degrees minus potential at 0 degrees. Okay, so that's what the work done is. Now what is that work done given? It is given to be whatever, that 24 into 10 to the power minus 5. That was that work done given. For the second scenario, I don't know the work and you have to move it from what to what? 60 to 120. So it will be 120 degrees minus potential energy at 60 degrees. Well, now what do you do, guys? Just calculate these values. It's very simple. U60 minus U0 is nothing but minus mb cos 60 minus plus, that minus and minus becomes plus, mb cos 0. Cos 0 is 1, cos 60 is half, mb minus half mb is half mb. So this is just half mb. That's what you get. And over here, this is minus mb cos 120 minus plus mb cos 60. Cos 60 half, cos 120 minus half, minus into minus plus half is 1. So it will be just mb. Don't you see this one is twice of the red one? This was half mb, this is 2 times of half mb. So how much should this work be? Obviously this one. As simple as that. Great. Enjoyed these questions. There is one bonus formula I'll give you, and you can use this very similarly to electrostatics. If you remember, electric dipole produces electric field and electric potential around it. Same way, what will a magnetic dipole do? It will also produce magnetic field and magnetic potential around it. The formulas are in fact very similar. If you have a magnetic dipole, north, south, if you are somewhere on, somewhere making angle theta with the magnetic moment at some distance, let's say r, then the formulas for field and potential, you can see it's very, very similar. Just that instead of 1 upon 4 pi epsilon naught, you have mu naught by 4 pi. Instead of electric dipole moment, you have magnetic dipole moment. And the rest of the terms are same. You had r cube below, okay? You have the same thing here. For potential, you have r square below. Remember that. It's very, very similar. Yep. I hope this is clear. No, Jagdish, work done by field will be negative of delta U, but that is the work done by the field. But here what I spoke was the work done by external force. So work done by external force will be plus delta U. Work done by magnetic force will be minus delta U. So that's the, yeah, yes, clear. So understand, potential has r square, field has r cube. Keep that in mind. Okay, a lot of people write r square here and r here. No, for dipole formulas, the powers increase by 1. Keep that in mind. Keep that in mind. The power increases by 1. Only for the dipole formulas. Okay, so very, very similar formulas. You can just, yeah, just remember this. That's all. Very good. So that's it for today, guys. And if you guys want to follow my lectures regularly, please understand we are coming on Catalysis for sure. But understand our regular classes, my regular classes are continuously going on VNQs. There is no point duplicating it, okay, in 2 channels. You might as well start subscribing and start watching the lectures regularly. There are batches for 11th, 12th and 12th passing out students separate. All live classes, even recorded classes are there from our previous playlist. For 11th, it is called Nurture. Okay, it's called the Nurture series. For 12th long term, it's called the Pathfinder series. And for the passing out students, we have the Rank Booster and the Zero to Hero series. So check that out. And obviously, time to time strategy sessions and motivational sessions and also some tips and guidance sessions are always there on the channel. And that's an exclusive English medium channel. Keep that in mind. We also have Hindi channel, English channel, which is the Vedantu JEE channel. So for all those English medium students, I would highly recommend you start following us on VNQs. Thank you, guys. And I know it was a long session, but I think it was worth it. Take care. See you again. And do let me know which topic do you want me to conduct on this channel ahead, so that, I can see your comments, and based on your comments only, I can probably guess what you guys want on this channel. So yes, let's do a marathon session again after a few more days. Take care. Bye bye. Leave your comments after the video ends. Hasta la vista.